Okay, so in preparation for our first big quiz next week, and this will be on integration and only integration. So remember, we have basically 5 different integration methods, and I will test you on those. So let's review those first. So the first one was substitution, and it is a very important one that you always have to keep in mind. Is it possible to substitute? Okay, but it's also shown that some of you still think too much that you can apply it all the time. That's not the case at all. Be very careful with it, okay? Then we had integration by parts. Again, be careful. This is not something that can be done that often, which we also called ILATE. The third one was trig integrals, which was kind of an intermediate step to the next one. So trig integrals involved trigonometric functions. The next one was the one that we're going to use this, namely trig substitution. And then finally we had the method of partial fractions. Okay, so in preparation for this quiz, as I said, this is from the material from before when we were doing online, face-to-face. You have your midterm. There is also, I will put up the review sheet from the final from the math department, the usual final of the math department. We would not have this now, we have our own final. But it is still based on what the math final would be. At least this part, big one, the quiz 1. Quiz 2 is going to be slightly different. So I will put this as extra material that you can go. There's the homework problems you can do, so go look at those. Also, prepare yourself for this quiz, right? It's not something, I hope you're not listening to this the day that you have to do your quiz. Do this in advance. Make sure that you have enough time to actually do all the work. Now, about this. So the quiz itself, there will be 4 questions, which is 4 times as much as the usual quiz. But I'm going to give you only 3 hours. So this means from, let's say, from 2 to 5 p.m. Okay. Now, the answers submit as always via email. But if it's 4 times as much, you're gonna have attachments 4 times as big, and some of you are sending me still very big attachment. So I would really try to keep attachments under 10 megabyte. But if you do this, and some of you even are already there with one quiz, so if you do 4 of them with 40 megabyte, I'm saying this because the email might slow down, or I might get this only later or never get this, depending on your email provider, etc. And your internet provider. So try to keep the size small. What are the 2 options you have? One option is reduce the size. That is, I posted a video. Go look for it. It's somewhere all the way on top of the page, where I'll post it also near the quiz. Where but I can only do this. I only know how to do this on an iPad or an iPhone. So if you have a different platform, you have to find it yourself. So reduce the size. Now the other option that you have, if you don't know how to do that, and by the way, it's often also, so preferably, instead of, most of you send me pictures, but you sometimes get PDFs. PDF, depends if you just take a picture and convert it into PDF, it doesn't really change the size, but you can also convert into PDFs. They are easier to deal with. I'm not requesting it, but you're going to take, most likely, more online courses. This is not going to stop in the fall, or even in the summer or in the fall. And some instructors will ask you to only submit PDFs. Some systems only accept PDFs. So it's a good thing to perhaps research how to do that. The other option you have is separate emails. I have no problem with that, so you can send me each problem separately, or 2 problems at a time, or something like that. It's also perhaps something you might consider doing anyway, to if you're running out of time, to make sure that at least your things that you think, okay, this one is fine, I'm going to send it out already, so that it's already out. That you don't, if you're rushing all the way on the end, and then all of a sudden you have like no time left, and you think, oh, I'm going to go be over time, and then you start taking pictures and things go wrong, you forget something or it doesn't go through. So perhaps better to already solve problems, say, okay, I'm pretty sure this is correct, let me send it out, okay? And you could still always afterwards send me an email and say, oh, I'm sorry, and afterwards I realized there was a mistake. Okay, you have the time from 2 to 5 to do this. All right, so that's the logistical bit. Now let's go back to our 5 integration methods. Some of these you can very easily recognize, and you should only consider these. This, of course, is always when dealing with the square root of a radical. Square root, not other roots. Sorry, I misspoke, right? I mean a square root of a quadratic. I said radical, but I mean quadratic. So only square roots and only quadratics. Anything else means a different method. Partial fractions are also easy to recognize. These are rational functions. Fractions of polynomials. Okay? So these two are, and of course trig integrals are just trig. So that's also easy to recognize. Substitution is somehow the hardest to recognize because what we look for is an inside function, right? And it's what you need is a good inside function, but in particularly an inside function whose derivative is basically what you have left. And then integration by parts, this is the ILATE principle. You have inverse trig, log, algebraic, trig, and exponential. And it's always a mixture of 2 of those. Now, mostly it's an algebraic together with one of the other guys. Okay, we have only dealt those guys. But I emphasize that in integration by parts, these other guys, the ILTE guys, have to be very simple. They cannot be themselves squared or in a radical or something like that. They themselves cannot have very difficult arguments. Inside of it, there can be perhaps an 2x, but not an x squared or anything more complicated. Okay, then it's definitely not ILATE. So I want to do put a couple of problems next to each other, and then let's go over them. What are they? So this is going to be, yeah, right. So how do you prepare for this? There are 2 things you have to do. Well, each of these methods you need to know, again, all the details of it. So you have to prepare yourself for those. I'm not going to spend too much time on that in this review. Most of what I'm going to do in this review is trying to tell you which method is actually the right one. Okay? So let's look at 3 examples here. I'll write them all 3 up first, and then we can discuss. Well, unfortunately, I'm gonna say, right, so, but think about this also all the time. Okay, so these are my 3 slightly different looking integrals, and they all will need a different method. Okay, pause the video, think about it yourself. Which method is each of these 3? Do this, right? Don't just listen to me, because you have to practice these things, okay? Just figure out what the method is. And okay, so I hope you thought a little bit about it. So let's discuss a little bit what is going on here. Well, here the first one, we have an algebraic and a trig function. So this is really ILATE. It really is ILATE, because we have an algebraic, that's the x, and the trig is the sine of x, and it's really just sine of x. Okay, so that's why I really consider this. And now remember, this is kind of a scale where on the left hand side is the u and the right hand side is v. So this tells me already that u is x and dv is sine x, and of course whatever dv is, the dx should go there. That's the one that we have to do. So this is, so once you recognize ILATE, you kind of have this recipe of how to do this. And now of course you have to carry it out still. Okay, that's the first one. Now what about this? So you say, oh, it's the same, it's ILATE, because it's again algebraic times a trig function. Well, it's not really a trig function. It's a trig function in which you have substituted x squared. That's not really a trig function anymore. Trig functions are just sine x, cosine x, perhaps sine 2x or something like that. But okay, so that's why it's not ILATE. It's this part is too complicated to be accepted to be work in ILATE. So what is it then? Well, let's see. It's clearly these two we can rule out because that's not of this form. Well, and also this one can rule out because there are other trig integrals are only trig functions. And by the way, they should never have an x squared in there either, so that's also ruled out. And we just said it's not isolate. So what is it? Okay, that's not hard anymore, right? So it must be substitution. So we look for an inside function. Now, there could be several choices. Luckily, here it's a kind of obvious choice. It has to be this choice, right? So if u is x squared, then what is it? What we do? Then du is 2x dx. Now, that's something that we almost have. We have x dx here. Oh, sorry. So we have x dx. These two together is almost this. So we're going to divide both sides by 2, and then it's equal to it. So it's very easy to solve this. So, okay, let's do this quickly. It's so easy to solve that I'll do it right away, right? So it is sine x squared has now become u, and the x dx is du over 2. And the antiderivative of sine is cosine minus cosine. Well, there's a half also, so divided by 2 here. And then do not forget, whenever you do a substitution, you have to go back to the original. So that is minus cosine x squared over 2. Now, sometimes in a substitution, so I'm going to add in a different color here a variant of this question. I could have also asked, okay, between, let's say, 3 and 5. Why not? Okay, so what is different then is you can do substitution, a definite integral substitution, if you then change the endpoints accordingly. So the endpoint x is 3 would now become u is now, you use the formula, right? U is 9, and if x is 5, u would be 25. So this means that in the new integral, when you do the u substitution, these endpoints should also become the u endpoints. So that is 9 and 25. Okay, and this means then that at here we can put these endpoints, the new endpoints, in u. We don't have to go to the next step. If you want to go to the next step, of course, then you have to put the original 3, 5 again. Okay, I'm not going to work this out. I hope it's clear what I've been saying, so I don't want to spend too time on little details here. Okay, so the last one, what is this? You could say, oh, okay, this must be again substitution. No, it's now sine square of x. Okay, and that's different. Sine x squared and sine square of x are different things. Sine square means sine x times sine x. Please also be very careful with manipulations that are completely illegal, so to speak, right? You cannot bring the x squared out of a sign or bring the square inside the parentheses. None of these rules are valid, right? So what we are left here is really a trigonometric function, a product of trig functions. So this is what we call the trig integrals. That's how they look like. Okay. So now, then we have to review all the different things. We have actually basically seen two different types of trig functions. Those that contain sines and cosines, and those that contain secants and tangents. Make sure that you know both, because they are very important, just on their own, but also they are important for this part. So they are twice as much important as the others if you want, because you have to use them there too. Because trig substitutions always will give you trig integrals. Okay, and so that's what so sines and cosines or secants and tangents. Sometimes you get a weird form, and if that's the case, you put everything in terms of sines and cosines, and then hope that it works. Well, normally it will work there, unless you made a mistake, of course. Right, so what happens here? Well, with the sine cosine, it's easy when one of them has an odd degree. It's a little bit trickier when they have both even degrees. Well, there is no cosine, so there's only sine here. So then remember what we have to do is the double product formula. That is that sine square x is equal to cos as a half, is equal to a half 1 minus cosine 2x. Okay, and so we plug that in, then get a half, which I can take out already, 1 minus cosine 2x dx. Of course, this is a simple form. Normally there would be more, right? There would be sine then cosine or something like that. And now you integrate, that's x minus, and the derivative of cosine is sine 2x. But now be careful. If I would take the derivative of sine 2x, I would get cosine 2x times the derivative of the inside function, so times 2. That I don't want, so I divide by 2. Remember, this is what we call compensation. So that's the solution here. And that's it. There's no need to work out anything else than this. Okay. So that's the trig integrals. As I said, I'm not going to go over all the possibilities here of trig integrals. I'll want to do one more list of possibilities. So again, try to test yourself what should be what. X cubed ln x to the fourth dx. X cubed ln x dx. And ln cube x over x dx. It's clear that we get not dealing with the last two types, or the last three types, right? So it's, these three are out here. So it's either substitution or integration by parts. Okay, so look at it, try to decide, and then pause the video until you figure it out, or perhaps even work it out. I'm not going to solve every single problem that I write down. I'll always set you up if you want to know what's going on, but the details I leave to you though. Okay, so the first one, well, okay, so it is between substitution and integration by parts. So is it substitution? Perhaps let's look for substitution. Are there good inside functions? Well, x to the fourth is an obvious, clear inside function. And I want that, because if I do that, then my derivative is basically what's left here outside my ln, namely this x cubed, 4x cubed dx. Well, okay, it's actually x cubed dx, so I should divide by 4 here. And so I can set this up. This is now, this whole x cubed dx is, so these are cancelled, is du over 4, and then the ln of u. Okay, now, what's the next answer? 1/4 of, who said, okay, I'm pausing the video, now look at it, who said 1 over u? Go bang your head against the wall, because that's not great, right? The derivative of ln u is 1 over u. What's the antiderivative of ln u? That's a bit tricky, right? What is that? Anybody remember how we did that? We have to do integration by parts again. It's a very special case of integration by parts. Where, let's think about, now, I don't want to work it out exactly here. Go look it up. It's actually, it's definitely one of the examples in the textbook. But I'll show you, it's very similar, namely, let's do, the third problem will be similar. So let's look at the next two problems. Let's look at the second one first. Is this integration by part or is it substitution? Let's ask the question, is it substitution? Well, in the ancestor of ln is an x. So x can, substitution, u is x, is kind of nothing, right? You don't do anything. You just say, you change the name of the variable, basically. So it must be a little bit more than that. Now, there's a product, and even sometimes an inside function could be a factor of a product. But what? If I take ln x, the derivative of that is 1 over x, is not x cubed. So no, that's not a good choice. Or if I take x cubed, the derivative of that is 3x squared. So no. So, okay, substitution doesn't seem to work here. Now, let's look at I late. Yes, that works perfect. Okay, so if I write I late, what do we have here? We have an algebraic, that's the x cubed. And we have a logarithm, that is the ln x. Okay, so we have the scale. This is the u, this is the v. So this time u is ln x. So let me do this in another color here so that we get not run. So u is ln x, and dv is x cubed. And as I said, we always have to put the dx with whatever we still dv. Why do we do that? Because if I take the derivative of u, d of u is 1 over x dx. And if I antiderive x cubed, because now I find v is an antiderivative problem, right? That is x to the fourth over 4. So the power rule for antiderivatives. Okay? And then we can work it out again. Well, perhaps let me do this, because here there's one step that sometimes people get confused by. So this is what the formula says it is to be. So u is ln x, v is x to the fourth over 4. It's easier to write this one first. minus, so v is x to the fourth over 4 times du, which is 1 over x dx. Now the one thing that you should not forget is when you have something like this, if there are powers of x multiplied together or divided by together, that means they can be simplified. And so, because there is no product rule, right? This can only be solved by making it in a single power, okay? So that would here now, of course, be, let me do this in a color. So if I calculate this x, I would do x cubed left. And now it's easier to integrate. I'm not going to write down the full final solution. So the last one, let's look at the last one. Again, we could think about integration by parts, but that doesn't follow at all, right? First of all, denominators normally is not integration by parts. By isolate, it sometimes is possible. In fact, with ln's, it is possible. So, okay. But the problem is that we have ln cube, and that is not allowed. I told you these transcendental functions, these inverse trig, logarithm, trig function, exponential functions, have to be very simple. They cannot be squares of that, they cannot be inside something else, and also their arguments cannot be very difficult. So isolate cannot work here. So it has to be substitution again. Okay, so if it's substitution, what? What is the inside? Well, sometimes the denominator is inside, but that's not a good choice. Well, sometimes the numerator is an inside function, but ln cube x, that the derivative of that is kind of complicated, because I'm thinking chain rule here, and okay, you can think about what it would be. So, but there is even something a little bit more inside, namely ln x itself. So here, it might take a little while to see this, but we have no other choice. We have to find it a substitution because nothing else applies. So u is ln x because du is 1 over x dx. Well, that's this one. And so now we see that's a third power of u. So this would become u cubed du. It's actually very simple. So which would be u to the fourth over 4, which would be ln x to the power 4 over 4. Okay? Or, yeah. Okay. So that's again shows you the differences, how you can try to figure out what is what. So going back to this ln u here, well, that's a very special case of this one here, right? Because in this state, here we had an x cube. In this case, we have an x to the power 0 if you want 1. So if you would have to solve this one, the dv would actually be just dx. And everything else is the same. Okay, so that's so far I want to say about these examples here. I will also give some test problems from the review sheet, final review sheet, that you can practice yourself a little bit more of these problems. Unfortunately, there are no good substitution problems. Okay, so you have to look for those in the chapter of substitution itself. Okay, then the two more problems that I really haven't discussed that much yet is the trig substitution. So let's look at these, because they have such special forms that you should recognize them right away. So here's an example. I'm just going to do one example, just to refresh your memory a little bit. So let's look at this one here. Okay, the first one with trig substitution is there are 3 forms. And they depend on, we have the trig identities. So let's write them first. Because it all comes from these trig identities. The first one that we have is cosine squared theta is 1 minus sine squared theta. The next one is tangent squared theta is secant squared theta minus 1. And the last one is secant squared theta is tangent squared theta plus 1. So now if you look at the shape of these things, it is 1 minus a square. This is a square minus 1. And this is a square plus 1, or 1 plus a square, because here the order doesn't matter, but in the previous two, since we're subtracting, the order matters. So this shape determines what the trig substitution will be, namely whatever is in the box, that will be my substitution. Now you might say, okay, this 9 is, well, there's only 1s here, what happens to the 9? So that might happen. Even things can be worse, right? It could be a trinomial where you have to complete the square. Let's hope that the instructor is not going to ask us this on the test. Okay, but with this one, that might be very well the case. So, what do you have to do? Well, we have to make that into 1. And how do we do that? By factoring out 9 outside the radical. Okay, so that's always the first step. So we have x cubed. Bring the 9 out of the radical. Now, the radical of 9, of course, is 3. So outside it becomes a 3. Now, how do you factor out something? That means you factored in each of the terms, right? So that's the result of factoring. Now we need, remember, this is what we need. A square. That's a square, right? You see. And so is this a square? Well, yes, it is actually x over 3 squared. And so now I'm saying this is my box. So my box, in the box is x over 3. Now where does it fit? It fits into this pattern. And so it tells me that my substitution, what is substitution? Well, this guy, right? Because that's what where the box corresponds to. So x over 3, the guy in the box, is equal to the guy that makes what makes the square here, secant theta. Okay, let's work it out. So once you have made this substitution, what you need to do? Remember, I'll write it a bit in steps here. Step 1 is we need to calculate, well, first of all, it's easier to get rid of these simple little fractions here. So write x is 3 secant theta. What we need to calculate is dx. So we have to take the root of secant theta. This is secant theta tangent theta, d theta. Don't forget the d theta. What I also want to do is make sure that what I have here, so let me rewrite. So what we had so far was we had the 3 that I take out, x cubed, and then radical x over 3 squared minus 1 dx, right? Oh, my dx was gone here. So I also want to make sure that that is radical is actually gone. And it's not a silly thing to do here because we often need this. So let's go over it. So we have radical, the x over 3, that was secant theta squared minus 1. Now we have our trig identity here, right? This is the trig identity. This is the square root of tangent squared theta. So this is tangent theta. Okay. Now we are ready to replace everything. So I'll go back in black. Step 2. Let's replace everything. We have the 3. What is x? Well, x is 3 secant theta. We have to cube that. So 3, what is that for a weird thing? 3 secant theta cubed. Don't forget that 3 itself also has to be cubed, right? Don't little things, but okay, you want to have full credit, right? As much as you can get. The radical we just calculated is tangent theta. And then the dx we also have here, let me do that in a different color, the dx comes from here, that is 3 secant theta tangent theta d theta. Okay, so let's gather all the 3's. We have a lot of 3's here, right? There's a 3 to the 3rd, 3 to the 4th, 3 to the 5th actually, which is 243. You trust me? Okay, that's what this is. And then what we have, how many secants? We have a secant cube. This gives me secant cube and another one. So altogether secant to the 4th theta, tangent theta, tangent theta, tangent squared theta. So let's first assemble all the powers, assemble the powers. Now we're going to think about a secant tangent. There are two things. Either I'm thinking of the substitution u equals secant theta, or u equals tangent theta. Now, what is going to determine my choice? Well, first of all, what is the du? In this case, the du would be secant theta, tangent theta, d theta. And in this case, it would be secant squared theta, d theta. So, whatever I do, I need either to split off a secant tangent theta or a split of a secant squared theta from this product that I have. But what I'm left with, everything has now to be, in this case, everything in terms of secants, in this case, everything in terms of tangents. And I know that I can do this because I have my trig identities, provided the powers are even powers. I cannot do this with odd powers because then I have to introduce radicals and, well, the whole thing was to get rid of radicals. Duh. Okay, so what is the options that I have here? If you think a little about it, so the option here is this one. And you could actually know because we came from secant theta, right? This is where we came from. And so this if you would do u equals secant theta, you basically would go back. Okay, so, but if you don't understand what I said, just figure it out. If I'm opting for, let's work it out. If I'm opting for tangent theta, I have to split off a secant squared theta. So one of the secant squared theta is going to go here. But I'm left with another secant squared theta. And so now I see that I'm correct, right? Everything has to be in terms of tangent theta. That's okay. Okay. This one not. This is something that is going to become the the du, or somehow my d fell away. And so this has to be transformed, but I can do this because of this triangle, this trigonometric identity. I'll do it again in a different color. So that is tangent squared theta plus 1. So we have here tangent squared theta plus 1. We have this tangent squared theta, and then we have this secant squared theta d theta, which will become, so this will be the du, and the rest will be u. So I get 243 u squared plus 1 times u squared du. Okay, 243. We have to expand this, that is u to the 4th plus u squared du. That is 243. U to the 5th over 5 plus u to the 3rd over 3. Plus c, I guess. That's what I want to write. Now, this is the difficulty of trig substitution. We have to go back all the way to x. So that's basically twice that we have to substitute back in. First the u, which is not difficult. U was tangent theta. So we get tangent to the 5th theta over 5 plus tangent cube theta over 3. Remember, that's how we write powers of trig functions, plus c. But that's not enough. This is tangent theta. We have to go in terms of x. Now, x was 3 secant theta. But the reason that I told you, do this radical, because then here it is. This is the guy that we want, and it's here. It's that radical. Okay? So this is now 243, and then we get the radical of x over 3 squared minus 1 to the power 5 over 5. You could write this as power 5 halves instead of the radical, but I don't care. Radical x over 3 squared minus 1 to the power 3 over 3 plus a constant, and that's it. Okay? Alright, now there could be a complication sometimes when the answer that you get here at this point, at this point you could run into problems when, suppose you are substituting with sines and cosines, then you wouldn't have tangents or something like that, and that involves this so-called SOHCAHTOA usage. Okay, so look it up how that works. Okay, that's one thing I wanted to show, and then I want to do quickly 2 examples of partial fractions. And this will be the only questions, right? I will be 4 out of these 5 types of integrals I will ask. I will not ask about Taylor polynomials, I will not ask about other stuff that we have done there, so only this, because that's enough. Okay, so the 2 partial fractions I want to look like, again, I'm not going to work it out every single one of them, but this one I want to do, I guess, more, is 4x squared minus x minus 1 over x squared plus 1 over x minus 1 dx. Okay, so step 1, well, okay, if the degree was too high, then we had to divide by it, but that's not the case. So, okay, let's keep on the steps as we had set it up before. So this is the crucial step here, is we have to factor the denominator. Now, how kind of me is that I actually did that for you? Well, at least partly, right? Because at least I have x squared plus 1 times x minus 1. So that's already factored a bit, but what about this guy? What do you think? That's not factorable, because this is a quadratic irreducible. So this is a quadratic irreducible. How do I know? Well, I can calculate the discriminant. Discriminant, that is b squared minus 4ac. So b, what is b here? 0, right? So minus 4, 1 times 1, which is negative. And a negative discriminant names quadratic irreducible. What does that mean? The word irreducible says it. You cannot factor it. So this is the end of the story. Okay? Some of you might think, oh, this is x plus 1 squared. No, it is not. Be very careful with that. So, once we have completely factored, and the factors have to be either linear factors or quadratic irreducibles, perhaps with powers of them, it could be several the same factors, but okay, what do we do then? We have to propose the partial fraction. By the way, there's also very early on I gave a review video on partial fractions, so you can also look at that one. So that's why I'm not going to do everything here. But I want to go through this one a little bit more. So what do we do then? Okay, we have these denominators. So these factors are denominators. But depending on the type of factor, there are two different things can happen. If it's a factor of this form, a quadratic irreducible, the first one, then it's of the form a linear, then on top of that you have to write a linear term, so ax plus b. If it's a factor where the denominator is a linear term, or even a power of a linear term, it has to be just a constant. And we go through the alphabet, right? Yeah, you might say, oh, don't we normally put this in the other order? Yes, but I'm being facetious and trying to do it the other way so that you see you can do it whatever way you want. Okay? Okay, so step 4, now we have to, so what is this? This is the original fraction, right? So sorry, I didn't write the original fraction. I should do that for x squared minus x minus 1 over x squared plus 1 x minus 1. So we clear the denominators. So this means we're going to multiply here with x squared plus 1 times x minus 1, x squared plus 1 times x minus 1, x squared plus 1 times x minus 1. So these x minus 1s here, this cancels. So let's see what we have. I get, and here of course, yeah, sorry, this whole thing cancels, so I have 4x squared minus x minus 1 equals ax plus b times x minus 1. Notice that I write parentheses here around my ax plus b. Perhaps if you want to really not forget this, you could have done this there already, so that you never ever forget this anymore, because otherwise you do get different answers if you don't work this out. And now what is left here, plus c, again, parentheses x squared plus 1, because I'm multiplying this whole thing. Okay, now remember, do not expand here. There is a method where you expand it. We're not doing this method, do this method. Okay, I would strongly suggest to do this. Namely, what we're going to do is plug in roots. Now that sounds very good, but there's only one root, because what are the roots? Well, we put this equal to 0. Now this is quadratic irreducible, so it has no solution, so the only solution can come from here. That means x is 1. There's only one solution here. But okay, we'll plug it in. So we'll plug it in the left-hand side, so it means plugging in means in there as well in there, right? So if I plug it there, I get 4 minus 1 minus 1, so that is 2. Now what do I get if I plug it in there? Ah, look, if I plug in 1 in this part, the whole thing is 0, and I don't, whatever I multiply with is 0, right? So I only have to plug it in this one here. So it is c times 1 plus 1. Oh, so c is 2c, so this means c is 1. I got already one of them. What about the other two? Now we are running out of roots, so if no more roots, then test points. Or test values, I don't know, whatever you call it. So x is values for x. So I'm going to take x equals, I think hopefully everybody said x equals 0, right? Okay, that's at least one choice, but perhaps it's not enough. Let's see, if x equals 0, I plug this in, again, in here as well as in there. So I get minus 1 is equal to, this is 0, so I have a b, and this becomes a negative 1, and then this becomes plus c times 1, so plus c. But I know what c is. So minus 1 is minus b plus 1. And so if I bring everything to the other side, let's see, I bring the b to that side, and so that's b there, so it gets b equals 2, right? I hope you see that. Okay. But that still doesn't give me a, so I will have to take yet another test point. Okay, so let's take another test point. I'll go black again. X equals 1, you say? No, because we have already taken 1. If you do the same thing, you're going to get the same answer. So you're going to get again that c equals 1. So we have to do something else here. X is 2. or minus 1. I'll take 2. So if I put it in the left, I get 16 minus 2 minus 1, so I get 13 equals, now I get 2a plus b times 1 plus c times 4 plus 1 times 5. Now I know what c is and I know what b is, so I get 13 is 2a plus 2 plus 5. Okay, we can bring 7 to the other side, we can 6 is 2a, and so you find a is 3. Okay, so the last step, step 4 or something, I forget now where I am, is the integration, right? So we have now that our integral is equal to what? Well, we now plug in everything, right? So ax, what was it here? Here. So ax plus b, that is now 3x plus b, what was b? b was 2 plus 2 over x squared plus 1 plus, and the other one was a 1, right? C, yeah, c is 1 over x minus 1 dx. Now, I want to do this part because remember what you have to do here now. This one is easy. That is just ln of x minus 1. Absolute values or not, I don't care. But this one here, we have to split. This x squared plus 1 over x squared plus 1 is the antiderivative of our tangent. But that is okay with the 2, but the 3x doesn't work here. So we have to split this as 3x over x squared plus 1 dx plus 2 times 1 over x squared plus 1 dx. I could have brought the 3 out here, so let me do that already. Okay. So I'm splitting this in 2 parts here, and this already I've calculated. Oh, plus ln of x minus 1. Okay. Why do I do this? Because this I will have to do with substitution. U equals x squared plus 1, namely the bottom, because then du is 2x dx. I have actually no x, so I divide by 2 both sides. Okay, so this becomes 3 times 1 over u du. Why over 1 over u? Because x squared is u, right? And what about this x dx? Well, that's all inside the du. And there was it over 2. Okay, what about this, the next term? This is just the antiderivative of this thing, is just arctangent, so I don't have to do anything here. So those two are done, and so now this one is now also done, right? It is 3 halves, and antiderivative 1 over u is ln u, plus, I'm not copying anymore, 3 halves, and what is ln? What is u? U is x squared plus 1, plus, and that's the solution. Okay, so I'm not going to work out the next one and just set it up. Let's see, the one I want to do is, where did I write it? This one here, minus x squared plus 5x minus 2 x cubed minus 2x squared plus x dx. Okay, again the degrees are okay, so step 1 is again nothing to do here. So step 2, we have to factor the denominator. Now this time the denominator is not really completely factored, so we have to look at it. Well, first of all, we have an x that we can factor out, so always do that first. That makes things simpler, right? So look, now we have a quadratic left. So 2 numbers that multiply to 1 and add up to -1. Or if you recognize this, it's actually a double product formula. So these are the factors. Now, it's instructive to know to write this as this way, because the x minus 1 comes twice, right? Because this tells us, this is important in the next step, the proposed fraction, or partial fraction, because we know that there is a special thing that we have to do here. So these factors are going to be no ones here, sorry. So I only wanted to write the denominators. X minus 1, but the factor comes to the square, so we also have a factor x minus 1 squared. Now, some of you might say, oh, we don't need this one because it's only x minus 1 squared. No, we do need that one too, so don't forget that, otherwise you're not going to get the right answer. You might think you get some numbers, you get a's and b's, but they are not the right ones. Okay, and what goes on top? Well, because these are all linear factors, all powers of linear factors, they are just constants, a, b, and c. So what is the difference here between this guy and this guy here, where we are, all the way here, is that this was a quadratically reducible, and therefore we have this linear part on top of it. This is a power of a linear one, and therefore we have a constant on top of it. Okay? Okay. And so now you work this out. I don't want to do this anymore. You have now two roots, x is 1 and x is 0. That means you're going to have to do one test point. You can choose whatever you want. And then you work it out. So I'm going to put here dot, dot, dot. This is something you have to work out yourself. And then this, I'll write down the solution here. If I did not make a mistake, what you should have gotten is minus 2x plus 1 over x minus 1 plus 2 over x minus 1 squared dx. And I'm just writing this down here, this part, because this, sometimes people make mistake of it. The first one is just an ln x, and the second one is also an ln x, but not the third one. There is a denominator, but denominators don't just mean ln x. That 1 over x, 1 over a variable, that is ln's. But this is 1 over a variable to the power 2. So this is actually, if you write this with negative exponents, this is actually this. And therefore we can do the power rule on it. So that is 2, add 1 to this exponent and divide by the exponent. Okay, and that's it. All right, so I'll post some more material on the webpage where you can try out yourself. I've told you there is this web work option that you have that I'm not going to pursue. Don't ask me about it because I don't know anything about it. You have gotten emails that should have explained how to do this. And you can test there, you can take several tests, practice tests, but it's not going to be your final. So, and for quiz 1, it's a good preparation, a decent preparation, not an excellent preparation, because the substitution part is a little bit weak in those test bank. Okay, so that's it.